All right, welcome back to General Chemistry, and we're still in Chapter 1 here. We've made it to the energy section, which is Section 5. So follow along with me while we talk about Section 5 and 6 and work some examples of the different types of problems. Now, I wanted to mention that I'll probably record one or two, maybe more videos of working homework problems at the end, to kind of give you a feel for what those problems look like, how to approach them, how to work them, and that sort of thing. We'll do more problem working in class, I hope, as long as we can cover a lot of the good concepts here in the video. So we've made it to Section 5, which is energy, and energy is a huge connecting concept between nearly every branch of science. Predominantly, the ones I'm thinking of, since I'm a professor of chemistry and physics, are those two. Alas, energy is super important. So let's talk about it and how it plays a role within chemistry. So energy changes in matter. So in physics, we define force acting through a distance as work, and there's a wonderful theorem that we get to look at talking about how work relates to energy. So changes in matter, both physical and chemical, result in the matter either gaining or releasing energy, and it's this amount of energy that allows then that matter to undergo a chemical reaction or to change a physical state or something along those lines. So energy ultimately is the capacity to do work on something. You may not have thought about it that way, but after discussing it, the connection kind of seems obvious. The ability, capacity to actually do some work. And if you look at yourself, you don't like to get off the couch unless you have enough energy to go and do something. And that something is sort of like work, and it requires energy for you to go and do that. And you have to sleep to recharge your energy so that you can have more of a capacity to go out and do some work. Now, typically, of course, we're talking about mechanical work, which is a force acting through a distance. And ultimately, energy then is this connecting concept between all of these things. So work is the action of a force applied across a distance. Like I said, this can be a push or a pull. Ultimately, that's how we describe a force. There are long-range forces as well, such as electrostatic forces or the force of gravity, that don't require a physical touch, like a push or a pull. Okay, so energy of matter. So kinetic energy is the first type of ultimately, if you think back to Einstein, you know probably E equals mc squared. That's energy equals mass times the speed of light squared, showing an interchangeability between mass, matter, and energy. So all matter in some way possesses some sort of energy that can be released in some situations. So energy is classified either as kinetic or as potential. There's a couple of different other types of energy that we'll talk about along the way, but these are the two most classic and most basic ones that you talk about, where kinetic energy is energy of motion and potential energy is energy of position. We know that energy can be converted into different forms. It can never be created or destroyed, only converted into different forms along the way. That's one of the laws of thermodynamics there. So when matter undergoes a chemical or a physical change, ultimately the amount of energy in the matter will change as well, such that the total stays the same. It just changes into different forms. So the kinetic energy, like I was mentioning earlier, energy of motion. So I told you in a crystal that the atoms or molecules vibrate back and forth still. And so this motion of the atoms or molecules or subatomic particles is all related to kinetic energy. Kinetic energy plays a big role. Thermal energy is a form of kinetic energy because you have to have this vibration that gives rise to the thermal energy. So it's heat energy, but heat is not such a good word to use here. Think about heat as the jiggling of atoms. So the more that they jiggle, the more heat, the more energy that they possess. And so therefore this molecular motion causes them to have more kinetic energy. Potential energy is the energy that is stored in the matter due to its position, or in the case of molecules, we're talking about chemical potential energy. So just by virtue of the bonds that it possesses and the different states that it's in at the time, give it its potential energy. So the composition of the matter and its position relative to other things, chemical potential can arise from a lot of different places, and it's a very important contributing factor when you go to study chemistry and atoms in more detail. So I told you that energy can convert into different forms, so you could, if you have the right apparatus to do so, convert kinetic and potential energy back and forth, and a lot of machines operate off of that process. My parents have a grandfather clock that has these big weights that hang down, and these weights slowly, by the force of gravity, are pulled down, and they allow the clock to run. And then after about a week, you got to take the weights and lift them back up so that they can regain all their potential energy, and they slowly fall back down over the course of a week, allowing the clock to run. And so that's an example of an interconversion between kinetic and potential energy. So all the processes that you have going on just convert energy from one type to another, and this is the law of conservation of energy, and is a very important law in thermodynamics, which we get to talk about more later, Chapter 6, Thermochemistry. So the other thing that's interesting about energy is it helps us to predict when something is going to be spontaneous, and this will come up a lot when we get to kinetics and equilibrium in general chemistry too, but it's worth talking about a little bit right here. So notice if you put this 10 kilogram weight at the top of the building here, and this is figure 1.10 on page 12, it's in a highly unstable potential energy, high potential energy position, so it's more unstable there. It likes to convert to kinetic energy when it's placed precariously at the top of a building. If it manages to make it back to the ground, it has a lower potential energy state and is therefore more stable. Okay, so materials that possess high potential energy are less stable in general, and processes in nature tend to occur on their own when the result of the material the result is a material with lower potential energy. So processes that result in materials with higher total potential energy do occur and can be made to occur, but generally do not happen without input of energy from an outside source. So you can have hydrogen and you can have oxygen mixed together in a wonderful balloon, and if you don't supply a spark, they're not going to combust. But if you do, then you took a process and you instigated it and you made it occur, even though it typically wouldn't have otherwise, getting energy from an outside source, the spark. So a process results in a system having less potential energy at the end than it had at the beginning. The lost potential energy is converted into kinetic energy, which then was probably released to the environment in some way through heat, friction, or some other sort of process. So during the conversion of form of energy, you could take this energy and use it to do work. So you have heat and you have work, and together these sum to make the energy, and you can use the energy that's there to do more work. So for instance, here's a car. You have molecules in the gasoline, which have the ability to combust, and you use the energy that's in those molecules of gasoline inside the internal combustion engine to produce a combustion, which moves the pistons, which creates mechanical work, which rotates the wheels and allows your car to go forward. And it turns out what you're doing is converting those molecules in gasoline, which are more unstable in terms of energy, into molecules of exhaust, which are more stable in some sense. So the energy is released and utilized to do work on the car, move the car forward. All right, let's talk about units. So this is section 6. Units are super, super, super important, and we need to get them right. We're going to use SI units. the International System of Units, which is commonly used among the majority of all scientists. Okay, and there's a few reasons for that. One of the biggest ones is probably convenience, since we can use the prefixes, and powers of 10 works well with scientific notation and those sorts of things. So it may take you a little while if you're not used to doing so, but try to get your brain working along the lines of SI units. That'll be really helpful for you. So the fundamental quantities we're talking about here are length. How long is something? That's the unit of meters. Mass. How much matter does it contain? We're going to use kilograms. Time. That's measured in seconds. That one's nice for us. And temperature. And technically, Kelvin is the temperature scale we should be using here. We'll talk more about that when we come to future slides. Okay, length. So normally we think of a yardstick. I want you to think of a meter stick instead. So a meter stick is 1 meter. Right? And you can see the relationship between them. I should note that the back of your book has some nice conversion factors for you to use. When you're working problems, these will help you convert between different units and whatnot. And I'll refer to them from time to time when we're working problems. So a measure of two-dimensional distance an object covers. Often we need to measure lengths that are not very long, lengths that are very short when we're talking about chemistry. Okay, the length between atoms, the distance inside of an atom, how big is an atom? I said on the order of angstroms, and their bonds. So we're going to be talking about short distances much more than we will long distances. So long distances would be like in astronomy when you're talking about distance between stars and astronomical units and really long distances. So meters sometimes will be a really big distance from our perspective in chemistry. So the SI unit is 1 meter, and it's about 3.37 inches longer than 1 yard. And it's defined as the distance traveled by light in a specific period of time. So that's a 1 meter. Commonly, we'll be looking at centimeters or other units. And remember, 1 centimeter, centi is a prefix that means 100th. So there are 100 centimeters to 1 meter. Or 2.54 centimeters makes 1 inch. Sometimes you may need to convert. And these factors are in the back of your book anyway, so you can look them up later if you need to. Mass. We said the unit was kilogram, and this is the amount of matter present in an object. That's its mass. So that's a little bit different than its weight, but it's still a valid thing to talk about. Okay, so weight measures the gravitational pull on an object, which depends on its mass. But if you put it in a place where the gravity is different, like on the moon, then it will weigh something different, even though it will contain the same amount of matter or have the same mass if you didn't change it. That's the difference. So our unit is kilograms. That's about 2 pounds and 3 ounces. And commonly we'll look at milligrams or even smaller types of mass. 1 kilogram is 1,000 grams. And so we'll be using grams. There are 1,000 milligrams that make up 1 gram. And we'll look at these prefixes in more detail coming up in the future slides here. Time. I said that the unit of time is second, and this is the duration of the duration of an event. How much time did it take? And we have a standard unit of second that your clock can tick away. So 1 second is technically defined as a period of time it takes for a specific number of radiation events of a specific transition from a cesium-133 atom. So there's this atomic clock that holds cesium-133 atoms, and after a certain amount of events, it calculates 1 second has passed based on that. It's a pretty cool thing. You should look it up. I once saw a picture of the guy who maintains the atomic clock, and the picture said, "Oh, the keeper of the time." And he was posed, and he was like this, and he had like 47 watches on each arm, and he was sitting here and he's got this big Flavor Flav clock around his neck, the keeper of the time. Anyway, a highly specified event in a cesium-133 atom makes up 1 second. That's just how we can look at it. See, the attempt was to take these units and to find something invariant, right? Before, it didn't quite make sense, because if the unit of length is this long and it's wood plank, or what happens when the wood gets old and it starts to deteriorate? Is 1 meter now this length instead of that length? Or it absorbs water and starts to swell. Is it this length instead of that length? And so we want standard units based on something that's not going to change. And one way to do that is to find a reference to something that doesn't change, like a cesium-133 atom, or how fast light can travel in a certain amount of time, and define 1 meter as the distance that the light traveled. And that way, it's not going to change in the future. Otherwise, it's not really a standard anyway. Why would you want to do that? Okay, temperature. We said the unit is Kelvin. So we have a couple of conversion formulas here at the bottom. And we're used to thinking in Fahrenheit, but it's easier to go from Celsius to Kelvin. And so typically we're going to, if we have a number in Fahrenheit, convert to Celsius and then convert to Kelvin, because the conversion from Celsius to Kelvin is just add 273.15. So technically, I told you earlier that temperature is the measure of the amount of kinetic energy caused by motion of particles. So a higher temperature meant more jiggling or more kinetic energy. And we were talking about how this kinetic energy, this energy is moving because of a temperature difference between different matter. And so this thermal energy change influences how much kinetic energy is there for different samples. And so we define heat as always flowing from hot objects to cold objects. So hot objects possess more jiggling, and cold objects possess less jiggling. And so the amount of energy is always going to move from those things that are really hot to those things that are cold. So a heat, ultimately, the heat, or the energy, if you will, is exchanged through these molecular collisions between two materials. So take a hot block, put it into regular air, and take another block at room temperature and set it next to it. Eventually the heat's going to flow from this warm one into this cold one, because the jiggling of all the atoms inside this block, even though you can't see it, as the gas molecules come and hit that block, they're gaining more of the kinetic energy because they're getting jiggled back. And so now this gas has more energy to move around, and some of those are coming and hitting this other block that's cold here. And slowly this block will begin to warm up, as long as your room's not too large to allow all the molecules to spread out and diffuse through the room. Okay, we're going to use these formula to convert between Celsius and Kelvin and Fahrenheit and Celsius along the way. So notice 1.8, and you may commonly know that as the 9/5. So you'll remember when you've done temperature conversions in the past, you had a factor of 9 over 5, and 9 over 5 is 1.8. So that's where the 1.8 came from in the bottom there, and that's due to the how the degrees line up on the Celsius and Fahrenheit scale. So take the degrees Fahrenheit that you have, subtract 32 and divide by 1.8, and you get Celsius. And you could algebraically rearrange that to solve for Fahrenheit if you're given a Celsius temperature instead. Well, your book doesn't list it in that way. So if you want to know Fahrenheit and you have a Celsius temperature, you take your Celsius temperature times 1.8 and then add 32 and you get to Fahrenheit. It'll be more rare to go that direction anyhow. You'll find these formula on page 16 of your textbook. All right, so the temperature scales are set up in this way. Notice where water is boiling and where water is freezing. So on the Celsius, that's 0 for freezing and 100 for boiling. That's a reason it's pretty convenient and we use it a lot. And when you convert to Kelvin, Kelvin has 0 set at absolute 0, so that makes it nice for us as well. And that's why a lot of formula need to have units of Kelvin in them when we're talking about temperature. You can see how Fahrenheit relates to that. Shouldn't shock you or be a surprise here. Commonly, we use Fahrenheit in the U.S. Celsius is used pretty much everywhere else and in almost every laboratory. And Kelvin is easy to get to. And another reason it's so great is because it has the absolute 0, a temperature you cannot get colder than, even though there have been some reports of negative Kelvin, but we'll save that for another day. Consider it to be an absolute zero. Okay, it's directly proportional to the Celsius scale, meaning a division on the Kelvin is equal to a degree on the Celsius. So that way they line up perfectly, and you just have to add or subtract 273.15 depending on if you're going from or to Kelvin from Celsius. Okay, and I'll actually show you where this Kelvin temperature scale comes from and how they can set absolute zero down there at minus 273.15 Celsius when we get to the gas laws chapter in chapter 5. Okay, so degrees Celsius is Fahrenheit minus 32 divided by 1.8. So a Celsius degree is 1.8 times larger than a Fahrenheit degree, and we got to account for that. The standard used for 0 degrees on the Fahrenheit scale is a lower temperature than the standard for 0 on the Celsius scale. So keep that in mind. 0 Fahrenheit and 0 Celsius do not line up on the scales. Okay, think about 0 Celsius, that's freezing, where water freezes. And where does water freeze on the Fahrenheit scale? 32 degrees. So those are the ones that line up, not 0 and 0. So don't let that confuse you. All right, Kelvin, I said if you're going to Kelvin from Celsius, add 273.15 because the size of the degree is the same on both of those scales. So although technically we should not say degrees Kelvin because Kelvin doesn't have degrees, we just call them Kelvin. So 1 Kelvin is 1.8 times larger than 1 degree Fahrenheit, because it's 1.8 times larger than 1 degree Celsius. And Kelvin and Celsius line up. Their divisions line up, I mean. Okay, 0 on the Kelvin scale is much, much colder than 0 on the Celsius scale. We know 0 on Kelvin is absolute 0. Okay, so here's some problems. Convert 40 Celsius into Kelvin and Fahrenheit. Why don't we work on this in the next video? So we'll come back to this, and then we'll talk about units a little bit more and reliability of measurements and those sorts of things.